Hi, my name is Jim, and today's topic is analog to digital and digital analog converters, which can end up being quite complicated. So we're going to start with a simple approach in understanding the basics and then kind of develop this into practical systems. So there's going to be two parts of this, and the second part will deal with some of the laws and restrictions and limitations with regard to noise and so forth, followed up by a visual and oral presentation of some of the distortions that can be produced if the laws of sampling and converting signals from the analog domain into the digital domain are not followed carefully. So we're going to begin here, and well, why do we want to do that? Why do we want to convert signals into the digital domain or back into the analog domain? And all we have to do is think about basically a CD for music. It starts out as an analog signal with, say, a band playing music, and it gets converted into a digital signal, and when it's converted, it's subject to digital processing, which nowadays is quite powerful. And one of the techniques on a CD is not only correcting errors in bits that can be caused by scratches, but by interleaving, which basically would stop a large scratch from interfering with many samples and destroying them. It's called interleaving. It's really pretty cool. And then once it's recorded, and when CDs were first made, the actual pits for the binary digits were the smallest man-made device on the planet. But when we play this back, of course, we want to listen to it in analog fashion with earbuds or headphones or whatever. So that's kind of a very practical example. Now, to explain this, we're going to start out with a circuit which is easy to understand, but really not very good from the standpoint of implementing it. And what we have is a collection of binary weighted resistors, 1, 2, 4, and 8K. And I'm going into an inverting summing amplifier. My inputs here are really controlled by digital switches, FETs if you will, that in this example are either going to put on 10 volts or 0 volts. And 10 volts is very not realistic, but it makes for nice numbers. This would be more like 3.3 or possibly even 1.8 volts. So in this, since this is an inverting summer, what I've concatenated to it is an inverting buffer with a unity gain, negative R divided by R, so our output is going to be positive going instead of negative going, which might produce some confusion. So to begin here, we're going to assign bits, and we have a most significant bit, and what we know about the operational amplifier is that there's a virtual short between the inverting and non-inverting inputs, meaning that this point here, for all practical purposes, we can treat as 0 volts, and that makes the analysis fairly straightforward. So what we're going to do is kind of use superposition on this and analyze one bit at a time, and then we'll kind of combine everything together downstream. So first we'll find the current flow for the most significant bit, and that's going to be bit number 3, and that's simply going to be equal to 10 volts. I'm going to let our input here be 10 volts minus 0 volts, so I'm including that negative 0 volts in there to show specifically that this is the voltage drop across the resistor. Mathematically, it doesn't matter. Going to divide it by the weight of the resistor. Our value of the resistor is 1K. We have 10 milliamperes flowing into this node, and that flows through the output resistor, also 1K, giving a plus-minus drop. And then what we can see is that we have 10 mils flowing through 1K, so that's going to produce a 10 volt drop across that resistor. Now, what's important is that this side of the resistor is anchored to ground, which means this side is going to be 10 volts more negative, which means the output of this is going to be negative 10 volts. Finally, when we go through the inverting buffer, that gives us a positive 10 volts at Vout 2. Similarly, we could take bit 3, and this is simply going to be divided by 2K, and bit number 2 rather is divided by 2K, bit number 1 is divided by 4K, and then the least significant bit, the one that contributes the smallest amount to the output voltage, is going to be the one with the highest resistor, 8K. So that for the LSB, least significant bit, will be 10 volts minus 0 divided by 8K. And then the contribution of that at this point would be a negative 1.25 volts. Then inverted would be plus 1.25 volts. So what we can see here is that we can effectively take binary weighting and produce outputs which correspond to the weight of the actual binary input. Now, this is all very nice, except manufacturing this in an integrated circuit is extremely hard to do, because the values of these have to be relatively close to their designated values, and meaning that for a 4-bit case, I mean, we're not really dealing with anything that's usable, but think about the 16 bits used in a CD player, for example. That requires a lot of resistors with very, very tight tolerances. Now, to get those tolerances would require, in the manufacturing of an integrated circuit, laser trimming and other techniques which basically would drive the cost way up. So when we actually implement this here, we're going to be using a different network called an R2R, whose precision, absolute precision, can be far off, but the precision between two 1K resistors made on the same die can be very, very close. So that's going to be based upon the ratio instead of the absolute value. So this is just kind of a learning example here, and then hopefully my intent is that you can see that these weighted outputs in fact produce what you're supposed to produce. So let's take our little binary weighting here and drive this by a 4-bit binary up counter. I'm using an HC161 here, and it's going to count from 0 to 15, so there's 16 permutations in this, and we're just going to let this feed our input here, and we'll take a look and see what happens. So same circuit as before. We have an inverting summer and then a buffer here with a gain of -1, and what we're seeing here as we up count, and what we're using is 10 volts, by the way, so this is not realistic. This here device is rated for 5, I believe, with a breakdown absolute max of 7, but I'm going to use it with 10 volts here so we can continue on with our example. So as we count up, we're going to go begin at 0 and end up going to 15. And as we do that, we're going to be applying 1s and 0s to this weighting network in 16 different possible ways, beginning with 0 and ending with 15, which is 16 permutations. And then what we see if we analyze this is that the least significant bit here, when we have 0, 0, 0, 1 binary asserted, is going to be the 1.25 volts. So every time we add an LSB to this, we're going to increase it by 1.25 volts. And then finally, when the count here is all 1s in hexadecimal, that would be F, we're going to be sitting at our maximum output, which would be the sum total of all of our bit weights, 1.25, 2, 5, and 10 volts. Those would be the respective inputs for QD being the most significant bit and QA, and when all of these are binary 1, we end up with 18.75 volts, and that's called the full scale of the converter. Now we also have a term full scale range, and the full scale range of this here would be 20 volts. What's the difference between full scale range and full scale? And the answer is 1 LSB. So if I have 4 bits and I have 1.25 volts per LSB and take 2 to the 4th power, 2 raised to the n power, where n is the number of bits, what I would end up with would be 20 volts, and I would call that full scale range, fully understanding that no input here can hit that. So this is just a terminology that associates with with the A to D and D to A conversion. So what we see is V out with the count moves up from 0 to a maximum of 18.75, and that's 4 bits. Typically isn't very useful in anything, but it's a good starting point. So just some language down here. Full scale range is VLSB times 2 raised to the number of bits, and find V out with a counter output of 8 base 10, and in binary that would be 1000. So we would just take our VLSB and multiply it by 8, which would be 1.25 volts per LSB times 8 LSB equals 10 volts. So kind of when we know an LSB is, we can find any other output without doing a whole lot of difficult calculations. Now, that was a D to A converter, and we're going to be mixing things up a little bit here. We can also use that as a building block for an A to D converter. So this is going to be our V in here that we're going to apply to a comparator, and remember that this is like an operational amplifier, except the output stage is designed to operate at 0 or 1, which means it's optimized to do that. The designers don't have to worry about linearity in a comparator because we're not dealing with an analog signal. And then what we're going to do is couple the output of this into a latch, and this will take a snapshot of the inputs when the output goes high. So this is a dynamic positive edge triggered input, which will cause the latch to latch. Then when it does latch, what appears at this side will be latched on the other side for further processing or whatever. So what we're going to do now is, taking a look at this, is what we remember is that if the non-inverting input is more positive than the inverting input, the output goes high. So we're going to take our stair step that we generated on the other page that I've kind of smashed in here, and this is going to be our input voltage appearing here, and then what we're going to do is simply out count or up count with the 4-bit counter and going through our binary weighted network here until we cross over the input voltage. And when we do that, the crossover point, the value of the actual count that's producing this, in this case it would be 8, because it crossed over between 7 and 8. So this would latch 8, binary 1000, as being the binary equivalent of the actual input voltage. So that's kind of nice. Issue in here is that I'm reading in between steps. So that's called quantizing error. And in a digital system, you can't have infinite resolution. In an analog system, it is infinite resolution. So the difference between what it is and what we say it is in binary is called quantizing error. And the way we can minimize that is to use more bits, so the step sizes would be smaller. And we would reduce the error between our input and our converted digital output by doing that. And of course, there's trade-offs. It's going to cost more money probably. And what we see is that effect down here. I've tried to recreate that between 7 and 8, and this difference here would be the quantizing error, and the QE can have a range of 0. That is, if the input voltage were right here, and it called that a 7, binary 7 would be 0 error, up to 0.9999 LSB. If it were really, really, really close to 8, but not quite, it would call it 7. It would call it 8. No, it would call it 7 because it hasn't crossed 8. So that would be the range of the quantizing error between this would be between 0 basically, and for all practical purposes 1 LSB. Other factors have to do with, is every step the same height? Well, no. And is every step the same width? No. So there's other considerations which we'll concern ourselves with later. So in this, what I'm doing is I'm showing the input voltage V is varying, like perhaps the top of a sine wave, and I've taken our steps, our 16 steps including 0 here, and I'm running them up, just showing them a straight line so I don't go through the tedium of trying to draw the steps. And what we're seeing here is that this is going to be, between the black dots, one conversion cycle. And here, it didn't have to count up very far until the output of the stair-step generator crossed the input. So it took this much time to convert. Here, since the voltage is rising, crossover occurs here, which takes more time for the stair-step to get up there. And here it's even worse yet, since it has to count up higher until the crossover. So what we kind of have in here is a problem with regard to timing, where the actual output is going to be dependent upon where crossover occurs. But the crossover can vary depending upon the actual input voltage. And that's not good. That's going to produce, if we were, say, to record this to store it in memory and then play back the sine wave, is these timing differences would produce something that didn't really look like a sine wave, and that means it would distort the sine wave. So we have to figure out a way of fixing that, and the solution to that is called a sample and hold, S&H for short. And what we have here is, this is the comparator on the other page, and I'm just kind of showing this as a block alone, and the only thing we're going to add to this is a capacitor in the front end and a FET switch. And this is driven by Vn, and Vn has to be fairly low impedance. So when a sampling cycle begins here, the switch closes momentarily, charges the capacitor up to the voltage of Vn, which would be at this point right here. Now what we can see is that process in red would be when it's sampled and that voltage is held on the capacitor. Sampled and held on the capacitor. So the capacitor is holding the input constant while the staircase is wandering up, counting up, looking for the crossover. So the output of the sample and hold is going to be a series of line segments that keep the voltage constant to not have the time skew that we had up here without the sample and hold. So that's kind of a nice way to fix it. Now, capacitors leak. Time constant tau equals R times C, so when we do a sample on this, we've got to pay attention to how large this capacitor is, what the impedance of the driving source is. FET switches like a CD4016, not that we'd want to use that, have certain channel resistances and so forth that has to be taken into effect. Further, since capacitors leak, the actual voltage would droop a bit. So droop is a term used in the language of sample and hold to indicate that it's not a perfect hold, and that will add to the error in the output. So as you can kind of see here, is that by the sample and hold, at least we're able to reduce the time skew. And also important is the output of our stair-step generator now occurs at the end of a conversion cycle. So we have common times here, and that eliminates this issue that we have up here. So by using S&H, we've made some progress. Now the good news is that a good number of analog to digital converters come with built-in sample and hold. So it's kind of automatic. We don't have to add parts to it, and consequential PC wiring, which is always noisy and has numerous problems. So again, this here represents the step output that we had on the other page, drawn as a straight line. Now, with regard to the binary weighted network, as I said before, it's very hard to get absolute precision in the integrated circuit process, but by taking ratios it's very easy to get good precision. And that leads us into what's called an R2R network. And basically, this is a 4-bit converter, so we can stay consistent with what we had before. We have a resistance R that might be, say, I don't know, 10K, and another resistor 2R, which would be 20K, and realistically the 2R could be made up of two 10K. Now, if the absolute value of this guy, the resistance, true resistance, say is 900 ohms, 2R would be 1800 ohms. If it's 1200 ohms, 2R would be 2400 ohms. But this process, it doesn't matter. It's just the ratio. So let's see how we would analyze this. And we have 4 bits here, and B0 is going to be our least significant input bit, and B3 is going to be our most significant input bit. And what we're going to do is use superposition to analyze this, and what we're going after here is B3, how much it corresponds to the actual Vout. What's its contribution to the output voltage? And then when we know that, it's very, very easy to fall back through this. So in using superposition, what I'm going to do is let the inputs be 0 or 10 volts. Again, I'm just using 10 volts because it's an easy number. And I'm going to let B0 through B2 equals 0 volts. So in superposition is you let one source be active and all the other sources be equal to their internal resistance. And with our voltage source here, B0 through B2, since they're driven by voltages, the internal resistance is 0 ohms. So I can conveniently connect these to ground, starting here, collapse the network. Now this may look kind of hard, but it really isn't once you catch on to it. So let's start with B0, our least significant bit, and work toward trying to figure out what B3 is going to contribute to us. So since B0 is 0, I've coupled that to ground, and what I see is that I have 2 resistors in parallel, which are 2R. So 2R resistors in parallel, 20K if you will end up giving us 10K. That would be the red guy. He turns into a single R, which is now in series with this R. So now looking at B1, we have 2R here, and we just collapsed B0 into this. So let's combine these resistors. So here's B1's 2R rather, and here's the 2R that results from the series combination of this. Again, what we can see is these 2 resistors, because the binary B1 is at 0 volts, is at ground potential. So we can take these 2 guys in parallel and again come up with an R. So this R corresponds to this guy right here, and this R is going to be everything on this side of the sheet. So let's collapse a little bit more. So this is the R feeding into B2, and this is the result of the collapsing we've done so far. And then combining this, we have our 2R here, and R plus R is 2R here, and this is the R leading into our B3. So since B2 is going to be at ground, I can connect him to ground and again see that I have 2R in parallel with 2R, which is R. Made that red, put them in series with this guy, and it all comes out to being, in the end, is B3 is feeding a resistor of 2R and 2R. So what we have here now is Vout is connected to the connection of the 2 points, the center node there, and it's simply going to be 1/2 of B3. So the contribution of B3 is going to be 5 volts. Now, once we know that, and keeping in mind this binary weighting, we could mathematically determine any output for any given input, or multiple inputs if we so chose. But once we know the MSB's contribution to V out, all we have to do is back up. B2 is going to be half of that, B1 is going to be 1/4 of it, and B0 is going to be 1/8 of it. And if we, say, run this full scale, where B0 through B3 are all at logic 1, which is 10 volts, is what we see is our total output then would be the sum of these, which is 9.375 volts. So full scale range is again 10 volts. Full scale rather, that's this guy. It's as high as we can go with all of the inputs equal to 1, is just going to be the full scale range minus 1 LSB, which again gives us 9.375 volts. So the R2R is very easy to implement in the manufacture of integrated circuits, and hence it's, you know, very, very popular. So let's progress a little bit. Now what we're going to do is take our R2R and going to run it through a 4-bit binary up counter as we did before. And just for the heck of it, as we're seeing the time here and the up count sequence going from 0 to 15, and each one of these steps varies by 1 LSB. And we end up with a full scale of 9.35 when the input to the R2R, or contrarily, the output of the 4-bit binary counter is all 1s. And then our full scale range here would be 10 volts. So it would be 1 LSB less than 10 volts. So this, we see 2 to the n minus 1 times VLSB, and 2 to the n equals 2 raised to the 4th power, because we have 4 bits, which gives us 16 minus 1 is 15 times the weight of VLSB at 625 millivolts will give us 9.375 volts full scale output. Now, this is kind of a verbose way to do it with these up-counting steps. So we have to, basically the industry did, figured out a better way to do it, and that's using a successive approximation register, referred to as an SAR, is a component that couples well with an R2R network. So if we just look at this for a minute, and using the stair-step ramp approach for converting, which, you know, we just covered with the steps and so forth, using 8 bits means that the up counter would have to count from 0 to 255, which is 256 permutations per sample. So that would be 2 raised to the 8 steps. And then what our hope is, and what has to be by design, is that one of these steps is going to cross the input voltage and hence cause the latch to capture what that binary value is. So if we take this and scale it into the real world a little bit, let's take telecom, a telephone company sample rates, and this is what happens when you call outside your local exchange, is your voice is converted into a digital signal, and it's sampled at 8 kilosamples per second, and they use 8 bits per sample, which gives us an ability to pass speech signals between 3.3 and 3.5 kilohertz. The absolute worst case on this is said to be 4 kilohertz. It's actually less than that by a sampling theorem, which we'll be talking about. So when you're speaking over the telephone, certain sounds you make, like an S where you're hissing, you're forcing air through a constriction, or an F, same thing, or a P with a pop, those sounds don't go through the network. The person listening to your conversation inserts them based upon the context of what you're saying. So it's not a flat network that carries all speech signals. But anyway, let's take a look at what this means from the standpoint of the clock frequency that's feeding our stair-step generator. So if we have 8,000 samples per second and we have 256 clock cycles per sample, and we multiply this together, we get 2.048 megacycles per second. And that's going to be the frequency that's actually driving the up counter. That's pretty high frequency. And we're only talking about speech. So let's just put this into context and talk about a stereo CD. And that sample that for commercial stuff is 44.1 kilosamples per second. And it's 16 bits linear pulse code modulation per channel. Now, all we're worried about is one channel, be it the left or the right. So if we take 2 rather, and raise it to the 16th powers, we get 65,536. And that would be the clock rate into the stair-step generator for one sample. And we're talking about 44.1 thousand samples per second, which gives us a clock rate into the stair-step generator of 2.89 gigahertz. That's pretty high, and it requires some relatively sophisticated integrated circuits. And to put that into context, a microwave oven operates at 2.45 gigahertz. So perhaps there's a better way of doing this besides the up-counting ramp. So let's take a look at how the successive approximation register would do that. So what we're going to have is our R2R network out here. We could use the binary guy, but let's face it, this is much more efficient, effective, easy to make, low cost. And we're going to feed it by a SAR controller, and the SAR controller has some elegance. It has some computing horsepower. And then we're going to take the output of the SAR controller that feeds the R2R binary network and pull these out, and that'll go to our latch after we do a digital conversion. So this is just a comparator, which is going to compare the output of the R2R as did before. Got the arrow going in the wrong direction here. It should be this direction, not in. And we've got our S and H sitting out in front here like we need to have. And what the SAR controller will do is it'll issue the MSB output from the R2R. Now, this red line here is our held voltage at the beginning of a conversion cycle. So this is constant, which is coming out of the sample to sample and hold register. It asserts an MSB and asks the question, did I cross the input voltage? Well, the answer is no. So the SAR controller then inputs the next highest significant bit and asks the question, did I cross the input voltage? The answer is yes. It deasserts this and inserts the next highest output voltage. And this would be like let me get my numbers right here. B2. Does it cross the input voltage? Yes. Deasserts this. Finally, it asserts B3 and B0, and we call that done. So this converges on the output in 4 cycles instead of 16. And it's all done by determining where you cross this, and the SAR has to be smart enough to know what it is. Now, this is going to pick a value which is actually less than the input voltage, and the difference here between the top of this and the red guy is going to be the quantizing error. So if we had an 8-bit SAR analog to digital converter, we could find the output in 8 iterations of the SAR controller as opposed to 64 up counts with the stair-step generator. So as you can see that the successive approximation approach is significantly faster. Now if we make n tries to convert V in, and for an 8K sample rate, using this instead of the up counter for the previous example, we would have 64K operations of this per second. So it's considerably better and used a lot. Now, one other flash converter we're going to talk about before I go on is called a flash converter, It's expensive and fast and draws a lot of power, and basically the way it works is it doesn't have to be clocked. There's a number of comparators in it. So for example, if I had, say, 8 bits I was interested in obtaining with a flash converter, is I'd either have 256 comparators, or they have a half flash, which is basically the same thing, but it's half the comparators, 128 comparators. And this is a linear divider network. VN is fed to all of the comparators, and say that the voltage were to be, in this case with just 4, somewhere in here, the output of these two would be high and the output of these two would be low. So what has to happen is this goes into a logic circuit to convert the input, which would be maybe 25% of the comparators are high and the rest are low, into a binary value. And the speed of this is basically the propagation delay of the comparators and the logic. Now, it may have an output latch connected to it, but flash is where you need fast stuff, and as you can see, there's lots of parts in it. Again, since we're using single value resistors here, the integration process can produce very precise resistors relative to each value, not the absolute value. Here we're looking at a 2-bit binary signal after it's been passed through a smoothing filter. Notice that the 0 is in the center of the waveform, so this is actually a bipolar waveform. Here we're looking at a 3-bit signal. It's quantized into 8 different levels, and again the 0 is in the middle of the waveform, giving a symmetrical response above and below, and then the red sine wave would be the reconstruction. What we're looking at here in the top picture in the blue waveform is the actual signal, and the red is the quantified signal, and down below is interesting. This actually shows the quantizing error, and on the left this is a function of the LSB, where 0 would mean it's exactly right, plus 5 would be an error of half an LSB off on the high side, and negative 5 would be half an LSB off on the low side. So what we see and can imagine here is that if we had more steps, the quantizing error would be smaller. This shows a fairly nice reconstructed sine wave. The original is in gray, and the quantized value is in blue, and the green at the bottom is the quantizing error, where the sample point misses the analog point by that much, and this is represented in LSBs. The top left picture shows a schematic of a sample and hold circuit. The switch is closed when the capacitor is charged to take the sample, and opened after, while a conversion, which would be to the left of A0, takes place. The arrows on the right picture show the point at which the switch is quickly closed and opened again that takes the sample, and then the picture at the bottom is the actual voltage which is sampled and held until the conversion takes place, and that's indicated by the dotted vertical lines. So that'll conclude with part 1 on this, and thank you for watching.